Dear students, this is my second lecture on NMR spectroscopy. In my first lecture on this topic, I have discussed about the basic principles and instrumentation of NMR spectroscopy. Go and watch that lecture, otherwise you will not understand this lecture. The link for the same is given in the description box. Moving on, in NMR spectroscopy part 1, we have learned that due to the spinning motion, a nucleus possesses a spin magnetic moment. The magnitude of the angular momentum of a spinning nucleus is described in terms of spin quantum number I, which is equal to the resultant of the spin of the individual nucleus. To find the resultant nuclear spin, which is described in terms of I, we can use the following rules. Nuclei with odd mass number have half integral spins. For example, proton, nitrogen 15, 19F, 31P, etc. have I equal to half, and that in case of 11 boron is equal to 3/2. Secondly, nuclei with odd numbers of both protons and neutrons have integral spins. For example, deuterium and nitrogen 14 has I equal to 1, while that of boron 10 is 3. These two types of nuclei can be considered as minute magnets having a magnetic moment and I is greater than 0. These nuclei are NMR active and give rise to NMR spectra. On the other hand, nuclei with even number of both protons and neutrons have 0 nuclear spin. For example, helium 4, carbon 12, oxygen 16, etc. have I equal to 0. These nuclei are magnetically non-active and are called NMR inactive and do not give NMR spectra. The values of the spin quantum number I are determined on the basis of some quantum mechanical calculations. To understand the pattern of NMR spectra of a molecule, we have to understand some terms which are shielding and deshielding, chemical shift, aromatic ring current, spin-spin coupling or splitting pattern, and coupling constant. Let us first discuss about shielding and deshielding. When an atom is placed in a magnetic field, the surrounding electron cloud induces a magnetic field in a direction opposite to the applied magnetic field. Therefore, the magnetic field experienced by the nucleus will be slightly lower than the applied field. The magnitude of the induced magnetic field is directly proportional to the applied field. Therefore, B induced is proportional to B0, or B induced equal to B0 into sigma, where B0 is the applied field strength in Tesla. Here, sigma is a constant known as the shielding constant. When sigma is greater than 0, there is a shielding effect, and when sigma is less than 0, there is a deshielding effect. The electrons are said to be shielded or deshielded depending on whether the magnetic field generated by the surrounding electron cloud opposes the magnetic field or reinforces the applied field. The effective field experienced by the nucleus is therefore given by B effective equal to B0 minus B induced, or B effective equal to B0 minus B0 into sigma. Therefore, we can write B effective equal to B0 into 1 minus sigma. Thus, the nucleus may be said to be shielded or deshielded from the applied field by the circulating electrons, and the extent of the shielding depends upon the electron density around the nucleus in a molecule. So the protons in different environment will have different shielding effect. For example, in case of ethanol, there are 3 groups of proton: the methyl protons, the methylene protons, and the OH proton. The three groups of protons will experience different shielding effect because of the different chemical environment. Here the OH proton is attached to the electronegative oxygen atom, therefore it is expected to be least shielded, and hence it has lower value of sigma. The methylene protons are close to OH group than the CH3 group, so it has lower shielding effect than the methyl protons. Hence the shielding constants for the three groups in ethanol are sigma OH less than sigma CH2 less than sigma CH3. Therefore, from the equation 2, it follows that B effective of the OH proton is greater than that of the methylene protons, which is greater than that of the methyl protons. Therefore, the field experienced by OH proton is greater than the methyl and methylene protons. For a given applied field, the OH proton will precess with greater Lambert frequency than the CH2 or CH3 protons. Conversely, in order to come into resonance with radiation of a particular frequency, for example in 100 MHz NMR spectrometer, the methylene protons require greater applied field than OH protons. The precessional or Lambert frequency can be determined as follows. Already we know that the energy difference between the two levels is given by delta E is equal to G and beta and B effective, from which we can write H nu equal to G and beta and B0 into 1 minus sigma. So therefore nu equal to G and beta and B0 into 1 minus sigma divided by H. Now simplifying this, we get 2 pi G and beta n by H into B0 by 2 pi, which can be written as nu equal to gamma into 1 minus sigma into B0 by 2 pi, where gamma is a constant and it is given by gamma equal to 2 pi G and beta n by H. This frequency is different for nuclei in different environment. Hence, the different nuclei come into resonance with different frequencies, and the precessional frequency of the OH proton is greater than that of the methylene protons, which is greater than that of the methyl protons. Okay, in order to construct NMR spectra of a molecule, you always remember that if there is a deshielding effect, then the NMR signal for that type of proton is observed in the downfield, and if there is a shielding effect, then the NMR signal for that type of proton is observed in the upfield. Okay, and also the number of NMR signals is equal to the number of different types of protons. For example, in case of ethanol, we have 3 groups of protons, so therefore we will get 3 signals in the NMR spectra of ethanol in low resolution as shown in this figure. So here the OH proton is attached to the electronegative oxygen atom, therefore it is expected to be least shielded, that means it is deshielded, so the signal due to the OH proton is obtained in the downfield. Okay, on the other hand, the CH3 proton is the most shielded, so therefore the signal for the CH3 proton is obtained in the upfield region of the NMR spectra. The second term that we have to understand to predict the NMR spectra is the spin-spin coupling or spin-spin splitting. Due to the interaction of the magnetic moments of one set of equivalent nuclei with those of another set, the lines in the NMR spectrum under high resolution splits into a number of finer lines which are called multiplates. This type of splitting is known as spin-spin splitting or coupling. For example, in ethanol, due to the presence of two methylene protons, the absorption peak due to the methyl proton splits into 3. With respect to a proton of CH3 group, the two protons in the CH2 group, each with spin half, can couple in 3 different ways, and corresponding ml values are +1, 0, -1, as shown here. The resonance absorption peak of CH3 proton is therefore splits into 3 lines having intensity ratio 1:2:1. Again, with respect to the proton of CH2 group, the 3 protons of the CH3 group, each with spin half, can couple in 4 different ways having ml values +3/2, +1/2, -1/2 and -3/2. The resonance absorption peak of CH2 proton is therefore splits into 4 lines having intensity ratio 1:3:3:1. On the other hand, the alcoholic proton is not affected by the neighboring protons because it exchanges its position so rapidly with protons of other molecule that it does not produce any splitting effect. Therefore, we can conclude that in ethanol, due to the presence of 3 groups of equivalent protons, we get 3 signals, and due to the spin-spin interaction, the signals of the CH3 proton splits into a 1:2:1 triplet due to the presence of the neighboring CH2 proton. Similarly, the signal of the CH2 proton splits into a 1:3:3:1 quartet due to the presence of the neighboring CH3 protons. The alcoholic proton, on the other hand, is not affected by the spin-spin splitting and it gives a singlet. The next term that we have to understand is chemical shift. The chemical shift is defined as the difference in absorption of a particular type of proton of a molecule with respect to the signal of a reference substance such as tetramethylsilane or TMS. It is denoted by the symbol delta, and mathematically it is given by delta is equal to nu s minus nu TMS divided by nu naught into 10 to the power 6 ppm, or delta equal to delta nu minus nu naught into 10 to the power 6, where delta nu is equal to nu s minus nu TMS and nu naught is the operating frequency. There are 2 scales that are commonly used to measure the chemical shift: delta scale and tau scale. Tau is equal to 10 minus delta. On delta scale, the signal for TMS increases downfield, and on tau scale, the signal for TMS is taken as 10 and it decreases downfield. The chemical shift of a particular proton is given by delta H is equal to nu H minus nu TMS by nu naught into 10 to the power 6. But we also know that nu equal to gamma into B0 by 2 pi into 1 minus sigma. So we can write delta H equal to gamma into B0 by 2 pi nu 0 into sigma TMS minus sigma H into 10 to the power 6. From this expression, we can also write gamma into B naught by 2 pi is equal to nu by 1 minus sigma. Since the value of sigma are of the order of 10 to the power minus 5, therefore we can write 1 minus sigma is approximately equal to 1. Therefore we can write gamma into B naught by 2 pi is equal to nu, which is equal to nu naught, where nu naught is the precessional frequency and it is equal to gamma into B naught by 2 pi. So we can write delta H is equal to sigma TMS minus sigma H whole into 10 to the power 6. Thus, as long as sigma H is positive, the chemical shift of a given proton decreases with increase in the value of the shielding constant, and thus it depends only on the shielding constant and it is independent of the applied field strength, and therefore chemical shift value does not vary from instrument to instrument. Tetramethylsilane is used as a reference substance in recording the NMR spectrum because of the following reasons. It is miscible with almost all organic substances. It is highly volatile and it readily removed from the system. It does not take intermolecular association with the samples, and most importantly, it contains 12 equivalent protons and highly shielded, and the delta value is arbitrarily taken as 0. Since it has 12 equivalent protons, so it gives a single sharp absorption peak. So due to these reasons, tetramethylsilane is used as a reference substance. But a major disadvantage of tetramethylsilane is that it is insoluble in water, and therefore we cannot study the NMR spectra of a sample using tetramethylsilane if the sample is highly polar and soluble in water only. An example of a polar reference substance is sodium trimethylsilyl propane sulfonate. This substance can be used as a reference substance if the sample is polar and it is soluble in water only. Now let us discuss the fate of an aromatic proton in presence of an external magnetic field in NMR spectra. In case of an aromatic proton like that in a benzene ring, the induced field opposes the applied field in the center of the ring, so we observe a shielding effect. On the other hand, outside the ring, the external flux density is parallel to the induced field, and hence the ring experiences a greater field strength than applied, and we observe a deshielding effect. As a result of this, the aromatic proton resonates at lower field, that means at higher delta value than other type of protons. Therefore, we get the peak for the aromatic proton at delta value around 7.0 in the NMR spectra. Our next topic of discussion is coupling constant. The spacing of the lines in a multiplet in NMR spectra is known as the spin-spin coupling constant. It is denoted by J. Its value is expressed in terms of frequency. The value of J are independent of the magnitude of the applied field strength. Generally, the difference in delta value of a multiplet is equal to coupling constant into 10 to the power 6 divided by frequency of the operating NMR spectrometer. It is found that the chemical shift value in Hertz are directly proportional to the applied field strength. From this lecture, we are able to learn about the shielding and deshielding effect, the chemical shift, spin-spin coupling or splitting with the help of the example of ethanol, the splitting pattern that takes place in NMR spectra, the aromatic ring current, and the coupling constant. Now I am giving you some rule of thumbs that are useful in predicting the NMR spectra of a molecule. The multiplicity of a given group of equivalent proton is clearly related to the number of protons on the adjacent atom. The splitting pattern that are produced by the coupling of protons can usually be interpreted by the following two rules. The first one is that if there are n number of equivalent protons that interact with the proton being studied, then the absorption line will split into n plus 1 lines. This is known as the n plus 1 rule. For example, the multiplicity of CH2 proton in ethanol is 3 plus 1, which is equal to 4, due to the presence of 3 neighboring CH3 protons. The second rule is that the intensities of the multiplets can be obtained from the coefficients of the binomial expression 1 plus x whole to the power n, where n is the number of equivalent protons. For example, in the methylene proton, that is the CH2 proton, the coefficients of 1 plus x whole to the power 3 is 1, 3, 3, 1. Hence the relative intensities are 1:3:3:1, right? So using these two rules we can predict the splitting pattern of the signals obtained in the NMR spectra of a molecule. Dear students, now you go through this lecture very carefully and try to understand the terms. In my next class we will try to learn how to predict the NMR spectra of any molecule by taking some examples. Also, we will solve some numerical problems based on coupling constants and logical problems based on NMR spectra. So, stay tuned.